Welcome all, it's Russ, and I'm here because I want to show you that I've figured out how to do logic circuits in Factorio trains, which I think is really, really exciting. Now, why would you do something like this? Well, I'm a computer scientist, and I love computer games. And so when I get an interesting computer game that's got dynamic elements inside of it, I immediately start thinking, what could I do with this that would be cool and different and, do something advanced that it's really not designed to do? You all have seen the 16-bit adder that somebody built in Minecraft, and I have immense respect for whoever that was because I think it's just an amazing accomplishment what they did. And I've seen people who have tried to do logic circuits in Factorio. I haven't seen anybody who's accomplished it fully according to the standards that I've set. If there is someone who's beat me to this, then I apologize and I'll be happy to give you credit in the description down below. But as far as I know, I don't think anybody has done this yet. I have a few rules here. First of all, when I'm going to do logic circuits, I want it to be completely vanilla. You will notice if you look carefully at my interface that I've got various mods turned on, but they're convenience mods only, just to make it faster to build, stuff like that. The actual logic circuits themselves are made of completely vanilla components. Second, it has to be no circuit networks. Again, when I show you my 16-bit adder, you'll see that I've got circuit networks connected to it, but those circuit networks are only there to monitor and to produce pretty lights that show what's happening in the system. They're not actually doing the logic themselves. Because in Factorio, the circuit networks are very advanced, and it would be trivial to do any sort of logic in circuit networks. That's not interesting to me. Third, it has to be absolutely rigorous. I've seen people who've tried to do this and they've gotten really close, but their version of logic circuits required timing. It required that there was that things would, happen at a certain speed, or you had to be at a certain research level. The trains had to be moving at a certain speed in order to make it work. I'm not willing to accept that. I want to be absolutely logically sound logic circuits, and I think I've accomplished it. While I've been talking here, I've been allowing a simple little logic circuit to run. There are two things that are going on that I will explain as we go through here. The train that's been moving past us on our left that has all the cars on it, that's the actual train that manages the logic for this particular gate. The train that crosses over it is what's called the clock train, because one of the things that I discovered was that I wanted, although I had the logic circuits working, I didn't have any easy way to know when they had completed a full clock cycle. So in a big complex system, what happens is that the logic train actually goes horizontally through every one of the logic gates in turn. And if you arrange it so that they happen in the right order, you can guarantee that data has flowed all the way from the inputs at the top all the way down to the outputs at the bottom. So when the clock train reaches the bottom, you know that the bottom now has the correct answer for everything. We'll show you how all that works in a minute. Now, let me talk to you about how I'm actually communicating values. I thought about a variety of ways to communicate values. So one of them was you could have a train, and that would mean a 1, and the lack of train would mean a 0. And I thought about that, but frankly, I couldn't figure out any way to make it rigorous. If you figure out a way to make it rigorous, kudos to you, but I'm kind of leaning towards the idea that maybe it's impossible. Second, I tried thinking about, if the train was moving in a certain direction, that would mean one thing, and if it moved in a different direction, it would mean something different. Again, I couldn't make it work. Maybe you can. What I ended up with instead was using block occupancy. And we're going to use block occupancy in pairs. Each of these pairs of tracks represents 1 bit of data. So these two here, these are a single bit. These two here are a different single bit. And what we're going to do here is that the left-hand track represents 0. So if you want to communicate 0, what you do is you need there to be a train on the 0 track. If you want to communicate 1, then you put a train on the one track instead. Oh, accidentally put down a pair. All right. So if you want to communicate one, you put a train on the one track instead. Now, an important invariant about how we're going to do this is that we're going to guarantee at all times that there's always a train on one or the other. This bit here is communicating the value 1. This bit over here is communicating the value 0. The key here is that these trains, I'm using these as input, these trains are never going to move. These trains exist only to occupy blocks. By occupying blocks, it will then force the logic trains, the ones that are actually performing the computations, down particular paths and particular tracks that will then force them to output other block occupancy. So what you'll see here is that whenever I've got inputs, I will put trains on the track sitting still. Those are basically hardwiring my inputs. When we look at actually I can show you this. Let's zoom out to map mode. When I've got my actual circuit, what you'll find here is that there are these 4 output tracks that I'll show you in more detail very soon here. There will never be trains on these 4 output tracks. But these tracks will either register as blocked or as not blocked, and that will communicate 1s and 0s. Now, how do you handle a transition from a 1 to a 0 and vice versa? So I said at all points there will be at least one locomotive in place, or at all points one of the blocks will be occupied. If we need to transition from one state to another, there will be a transient state where both of them are blocked. But then eventually the second train will be removed. So what we're guaranteeing is the one thing that's an invalid state is for both of them to be open. That's never correct. Now, how are we doing this? I can show you the quick summary here. What you'll notice here is that I've got a big circle train here it's got very long, so it can occupy lots of blocks, and it's going to go in a continual loop here. I've got a pair of stations back to back here called cycle A and cycle B, just so that we can force the train to go in a continual loop. I've got a requester chest that's feeding rocket fuel into the train so that it will never run out of fuel. And yes, I use cheat mode in order to get an infinite supply of rocket fuel. But this is that's a standard requester chest. So I've just over somewhere in the map, I've got a cheat mode chest that gives me infinite rocket fuel so that all the trains can stay fueled. You'll also notice if we take a quick look at the clock train, which is this lower loop here, it similarly has cycle A and cycle B with a requester chest for fueling it. In a more complex system, this clock train would traverse an extremely long circuitous route through all of the logic gates one at a time. Right now, because I'm showing you a demo with a single train, single gate, it's very, very trivial. Now let's see now how we read our values. And this is one of the central elements of this whole system. What we've got here is that we've got a train that's approaching a chain signal. And what you'll notice is that I'm going to use heavy use of chain signals throughout the whole system. If you're not a Factorio expert, I'd be happy to make a video about that later. But right now what I'll tell you is that a chain signal is a signal that will not allow a train to proceed unless it can find some place to go. So essentially, if you have a whole bunch of chain signals all in a row, the train has to plan out its entire course until it gets to an ordinary signal at the end. And it will only proceed into a section of track if it can go through all of the chain signals and pass through all of them. It has green on all of them, and it has green at the ordinary signal at the end. So that means that you can prevent a train from even starting to move until you know exactly where it's going to go. The second thing that's very, very important with Factorio, or for making this logic work, is that when the train actually crosses that signal and begins to move, it has already pre-allocated all of the blocks that it's going to need in order to get through this whole complex layout. So although the train is not yet at the place where it's going to be in the future, in terms of block occupancy, in terms of the signaling system that Factorio trains use, it looks as if it's already there. That's very, very key here, because this train that's circling is going to look as if it's holding blocks open even when it's not physically inside them. All right, so what do we have to do here? We start with a single track here. So this is sort of the reset point of any calculation. And we diverge into two. We have a chain signal before it, so it has to make the choice of which of the two paths it's going to follow before it passes the chain signal. And what I have here is this is reading the 0 wire and the 1 wire for a single bit. And what you'll notice, the way I've got this arranged here, is that if the 0 wire is occupied, then this block will be blocked and the train can't proceed through it. However, if that was blocked, this is free, because this vertical track only crosses one of the two tracks. Then the 1 wire does the exact same thing, but on the flipped track. And so by definition, what happens is when the train gets to this point in the calculation, it is either sitting on this track, which means it went through the 0 wire, it crossed the 0 wire, or it's going through this track, which means it crossed the 1 wire. Now we have to think in backwards, right? Because this train here means that we're communicating the value 0 to our train. Our input is 0. And so when we see that the train avoids the 0 track, that means it has read 0. So if the train gets to this point in the system, then we know that we've read 0 from the input bit. If the input bit was 1, then we get to this point. Now, if we're ever at a point where both of these are blocked temporarily, then there will be no possible path. And this train will continue to wait at the signal back here until one of those two paths becomes available. Now, what happens next? This is a 2-input gate that we've represented. So we have to read the other input as well. And what you see is that each of the two tracks here splits again. And now what I've got here is that I've got these two tracks. These two tracks represent that we would cross the 0 bit on the second input. But you'll notice that there's one of these represents that we also that we crossed the 0 bit. Okay, I gotta get my head around this. If we cross the 0 bit here, and we also want to cross the 0 bit here, then it will proceed through this track, it'll be down here, and then it will eventually go here. So this piece of track right here that I've just highlighted represents that we crossed the 0 bit on both of our inputs. Therefore, the inputs both represented 1. This is the 1-1 read. This is the read that says we first read a 0 because we had to avoid the 0 wire, but now we're willing to cross the 0. So this is a 1-0. I call this 1-0 because I think of this as the least significant bit and this is the most significant bit. So this is the 1-0 track. This is the 1-1 track. What is this? This is the 0-1. No, this is the 0-0 track because it had to avoid 0 here. It also had to avoid 0 here. This is the 0-1 track because we avoided the 1, but now we avoid the 0. And as a result, you'll see we then do crossovers again, and we're reading the 1 bit off that same one. And now what we have is 4 different tracks representing the 4 different possible input states. This is what happens if the inputs are 0-0. This is what happens if the inputs are 0-1, if the inputs are 1-0, and if the inputs are 1-1, or 0-1-0. 2, and 3. And if we go and we double check, look at that. We did have our input set to 0, 0. All right, well, let's just sanity check to make sure that it works. Let's go over here, and we will change our first input. So now that what we're going to read is a 0, 1. Now, things don't get updated quite yet. We're going to have to wait for the train to come. But what we should see is that the train should now go through here because the 0 bit can be crossed, and we need to avoid the 1 bit. So watch what happens. The train does exactly that. It still has to avoid the 0 wire here, and so it ends up on track 1. All right, so what this means here is that now we have a general purpose way to read arbitrary input signals. I'm showing you a 2 input. I have built 3 input. You could make this as large as you want. It's just basically on available space. You could make you could have as many inputs as you want and just encode them into a whole bunch of different tracks here. Now, how are we going to do output? Well, we're going to use the exact same trick in reverse, because what's going to happen here is that each of these tracks is going to be fed into a track down below that's going to collapse values down towards that single track again. And what's going to happen here is that we are going to write outputs by choosing to cross or not cross certain blocks. So for a really trivial thing, what I decided to do in this case, let's see, how did I wire this up? This is, remember, this is value 1, so it's 0, 1. Our first input was 1, our second input was 0. It sends it down through this track. So this blocks the 1 wire in our output, in the right hand, the most significant bit of our output. But as we follow the track, what we find out is it blocks the 0 bit of our left hand output. So what we've essentially done is we've taken a 0, 1 value and we've essentially swapped them. Up at our inputs, we had a 1 on the left, a 0 on the right, meaning our least significant bit was 1. Here, our most significant bit is going to be 1. But what you realize here is that these 4 tracks here, these 4 tracks represent 4 different conceivable outputs. And that means that we've got 4 different conceivable outputs, and we've got an enumeration of all the possible inputs. We can now wire up essentially a truth table. Let's do a 2-bit NOT gate. So we'll negate both of our outputs. All right, so if both of our outputs were set to 0, if both of our inputs were set to 0, then both of our outputs should be set to 1. All right, so how to do that? Well, what you can do is you can read it. In order to set 1, I'm going to need to come through this track. And in order to set 1, I'm going to need to block this track. So if you follow it through, what you'll figure out is that this is the track I need to run on in order to turn both bits on, to set both bits to 0. So what I'll do here is I'll build a connection. And now this says that an input of 0, 0 will produce an output of 1, 1. All right, how about an output or an input of 1, 1? An output of 1, 1 should become, you know what? I think I didn't look carefully enough at the gate. I think the way it was previously wired was a double negation. It wasn't actually a swap. It was a double negation. All right. Well, I had just thrown it together as an example, so I hadn't looked real carefully. Okay, so this represents inputs of 1, 1. We want to write 0, 0. So we want to write to here, and we want to write to here. In order to do that, we need to connect to there. Yeah, I think, I'm not sure yet, but I think it was just a negation. All right, now this one's a little weird. So this is 0, 1. This means that the left hand was 1 and the right hand was 0. All right, so we want the right hand, we want the left hand to be 0, the right hand to be 1. All right. Left hand 0 means we need to go through here. And right hand 1 means we need to go through here. Yep, that's what it was. All right, so this is kind of the cool thing, is that you can build arbitrary connections here. All right, so we've just wired it up. How about something that just ignores all outputs and it always puts out 1, 1? We could do that. That'd be a weird thing to do, but you could do it. To output 1, 1, we want to cross this, and we want to cross this, which means we have to connect to this last track. So you can connect like this. Whoops. Want to delete, delete. And now we should be able to just copy, paste, paste, and paste. And now all possible outputs go to the same thing. And you can see, of course, that we could have a 2 input, 1 output quite easily. It would just mean that we'd basically skip this whole section. We'd just have everything feed into a pair of tracks. Likewise, you could have more outputs than you have inputs. That would be strange, but it could be done. There's a variety of things you could do. How do we actually make all of this work so that we never actually clear any of these signals? The first thing that you notice here is that I've made the train very carefully long enough so that it will always foul the last lines. And I actually went through and I tested it in all possible paths here and all possible paths here to make sure that this train was just long enough so that when it came to a halt over here at the station, it would still be literally sitting on this block. It's physically blocking all the paths. But let me go one step further and show you a little bit more, because you had to do something even a little bit trickier than that in order to make it work. In order to make this work, let me delete all this so it won't advance. So now we're going to watch that train. It will advance up to the chain signal. Actually, it says no path. If I do it like this, I will give it a path that's plausible there. Okay. What I just did here is now there is a plausible path, so it advances to the signal. But the signal will never clear, because on this one path that's possible, it will always have some blockage here that it cannot advance through. And what you'll notice here is that while it's sitting at the chain signal, we still have fouled this wire. So this wire will continue to show a signal, and so will this one. How do we continue to communicate those values while the train is in motion? Because if the train advances just a little bit further, this car will come off of this position. In order to show this, I'm going to have to see if I can get my timing right here. All right, let's put those back in so that it will run. And actually, I want all of those to be back the way they were. Okay. To show this timing, I'm going to have to come up here and block the path and actually cause an accident. The reason I'm going to do this is because if you simply stop a train, it loses all of its allocations that it's placed through the chain signals. But if you cause an accident like that, then it still holds the allocations. All right, so if you take a look at this, what you'll see is that it's got a yellow signal here. Yellow in Factorio means that it's a pre-allocated block. And so it has pre-allocated the entire path. In fact, if I put my mouse over the train, it'll show you the path that it's already planned ahead for. That path extends through chain signals all the way to here. I don't get ordinary signals until basically I'm back at the station again. And so what's happening here is that although the train has moved out where it's no longer physically fouling this line, it is now virtually fouling it because we've pre-allocated all of those chunks, all of those blocks for the train to eventually move through. So if we have this train and its inputs are not changing, then it will permanently block certain output certain output lines. If the inputs change, then what you'll find is that there will be a transient state where it physically blocks one block and it's virtually blocked a different one. So let's go here and let's move this back to the 0. So now we're going to read 0, 0 out of the system. Now this train has already figured out what its plan is. So I believe that it won't. Yeah, see, it went through this block even though it was occupied, because it had pre-allocated it. So let's cause an accident here. And now what you'll see, that the train is sitting on this upper path here, but it has pre-allocated a different one, because now it's planning to have different sets of outputs. Now, when you start chaining these logic gates together, there can be interactions between them. So you can have a system where it's trying to change a particular output to a new value, but it can't take the block because the other block is still occupied. This is why you'll notice that there's a little bit different about how we've got this set up. We've got this arranged in such a way that the train will definitely always hold the output lines steady. Those never come unallocated. However, you'll notice there is a window of time when the train is down at the bottom of the track where it's possible for the other signals coming into the logic gate to change, because the train does not permanently block its inputs. It only permanently blocks its outputs. So this means that now you can have logic gates above you that will change their state while you're down in the bottom half of the track. And then you read them, and that produces a new output that you're going to produce out of the bottom of your gate. Now this comes to where the clock train works. There's another detail about the clock train. What you'll notice here is that if I'm very careful about how this runs, I may have to run this by hand in order to make this work here. We'll switch this to manual mode once it's figured out. All right, so there are two places where the clock train crosses the logic train. It has to cross over here. It obviously cannot cross over here while the train is over here making its way through the inputs. Because the train will have pre-allocated its entire path. So, but there is a window of time where it can cross. The way it can do that is that it can cross when the train leaves this physical block. So I've carefully tuned the train. It needs to be long enough so that when it's sitting at the station, it's still actually, even when it's sitting at this signal, it's still physically fouling the outputs. However, it has to be short enough so that it's possible for the clock train to advance. And so if we advance it here, what you'll notice here, we were physically holding this section of track up until the point that we actually crossed over the clock train the second time. But now that we've advanced past it, what you'll find is when the logic train comes to a halt at this station, that allows the clock train to advance through the right-hand part of the circuit. Now, that's a very, very small window of time. The only time that the clock train can advance is when the logic train is somewhere in here, which means that we're approaching a station, but we have not yet read an input. This is before we read an input. But as this train now starts to advance here, the clock train cannot advance. The only way that the clock train can advance is now the clock train, in just a moment here, is going to become unblocked. Now, right about... Oh, there's the signal there. All right, now it's allowed to advance. Now, because I'm running in manual mode, what you'll see is the clock train just circles endlessly. Oh, actually, I don't have signals there. So that actually doesn't occur. Never mind. Okay, but anyway, the point here is that the clock train cannot... the clock train, in order to make a complete pass through the logic gate, it has to go through two different states. First, it has to be in the before the logic train read its input state. And then it has to move to the after the logic train read its inputs. In other words, by the time the clock train has gone through this loop once, you know that the logic train has read its inputs and has set up a new signal based on those, a new schedule based on those inputs at least once. Now, in reality, it might happen many times, but it has to happen at least once. You'll also see that there's a little issues like the clock train crosses here. And so the clock train actually would block the ability to send values down the line, right? If this was crossing and this was also crossing, then there was no way that we could send independent 0 and 1 values. That wouldn't work. So in reality, what happens is that the clock train is a little bit different than this. What happens generally is that there might be a whole row of logic gates with doing some, whatever calculations they're going to perform. The clock train will run all the way through them, and when the clock train has run all the way through those logic gates once, then it means that it has performed the complete calculation on that row. But then what will happen is that it actually loops around and it comes back. What you would generally see here, if the clock train would come through, it would go through the self loop, it would come back in the opposite direction, and then this would actually take it to the next row of computation. If we want to do something where just with this single gate, then we'll just put another self loop in there, and now it'll advance just fine. Can we do an adder? Can we do the classic? Well, let me take you over there and I'll show you. Okay, I was going to do this off camera, but then I realized I want to be able to run through and show you the various bits, and that's going to take a long time. So I use creative mode to crank up my speed. I've got over here some lights that are showing what we're adding up, but let me just show you the basic things here. This is an adder that although I don't have subtraction implemented, it was designed for allowing subtraction, so it has a carry into the 0 bit. Here I have the A and the B inputs. So in this case, I've set both of them to 1. All right, and what I have is a logic gate here. This is a full adder. So it takes an A input, 0 and 1, takes a B input, could be 0 and 1, and it takes the carry bit. It produces 8 tracks of possible values. Now, a full adder creates 2 outputs. It creates a sum and a carry bit. And so the sum bit is here. The carry bit is here. And so what I have is a very long train that will foul everything just the way I said it should. You'll notice here's that self loop for the clock track. Over here you can see the clock track proceeding on to the next line. And so what we have here, if I can look at it, this is a full adder. It has 3 inputs, it has 2 outputs. It's guaranteed to always produce the proper result. The sum bit is produced. Notice that there's not a train here, but block occupancy can still read it. So what did we have? What were our inputs originally? We had 1 plus 1 with a carry in of 1. So our output for this column should be 1, 1. Well, what do we actually see? What we see here is that the 1 bit of the sum was blocked, just the way we would expect. And what we also see is that the 1 bit of the carry was blocked. So the second one, we've got again 1 and 1. So this is 1 plus 1 plus 1 will give us 3. And so this will read, this is our second train. This again reads the same values. We have a 1 as the output, and you'll notice that we're going to be blocking the 1 line again. And so what I've done is I built a 16-bit adder. There's level 0, 1. There's bit 15. I hope this was interesting. I hope it was a lot of fun to watch. It was a lot of fun to make. I'll see you later. Bye-bye.